The next important circuit element we want to talk about is a resistor. And so again, let's start by sort of coming up with a pretty basic definition for what a resistor is. Well, fundamentally, a resistor is a device that opposes current flow. So it's going to resist how much current can flow through it. So if we start with the most basic picture we can create for a circuit with a resistor, again, we've got our single battery sitting over here, positive terminal of the battery, negative terminal of the battery, and all we've done is we've taken some ideal wires and connected that battery to a single resistor. Well, when we do that, of course, what's going to happen is current is going to flow through the circuit. Given our convention for treating current as if it is positive charges flowing around the circuit, we're going to have current coming out of the positive terminal of the battery, flowing clockwise around the circuit. It will then flow across the resistor before flowing back into the negative terminal of the battery. So we will have current that circles clockwise around the circuit in this particular configuration. So what we want to know, of course, is how can we relate the voltage across the resistor, the current flowing across the resistor, and the resistance of the resistor as it sits here within this circuit. Of course, that is given by Ohm's law. So Ohm's law is the fundamental relationship that defines resistors. So there is some potential difference across the two ends of the resistor. The potential up here as the current enters the resistor will be different than the potential down here as it leaves the resistor. That potential difference across your resistor is going to be equal to the current flowing across the resistor times the resistance of the resistor. Now we're going to do what we've typically done, which is, again, we're just going to sort of drop the delta. We'll write this out as V equals IR, and of course this is Ohm's law. So Ohm's law tells us how these three important parameters relate. Just remember, of course, that this is the potential across the resistor, the current flowing through the resistor, and the resistance of the resistor. In this case, because we only have a single resistor connected to our battery, the potential difference across the resistor is the same as the voltage of the battery. So here's a situation where this V here is the same as the voltage of the battery. Just remember, in Ohm's law, that equation, this is really the voltage across the resistor, not necessarily the voltage of the battery. That'll only happen in very special circumstances where there's only one element in the circuit. Well, I can take this equation and solve it for R to, again, think a little bit more about what the resistance means. When I do that, I get that R is equal to the potential difference across my resistor over the current that flows through it. So you can think of this as what the resistance of your circuit is telling you about is how much voltage does it take to drive a given current. Right? The more you increase the resistance, the more voltage you're going to need to get a particular current. Again, the less you increase the resistance, the less voltage you'll need to get that particular current. The other way to think about that, of course, is, well, if you fix the voltage, the higher the resistance is, that means the less current flow you're going to get across your resistor. And that's the one that sort of makes more intuitive sense. In general, for most materials that we would make a resistor out of, they fall into one of two categories. They're either what are known as ohmic materials or they're non-ohmic materials. If we think about Ohm's law, right, we can think about this as Y equals, we put the M over here, we put the X right there. So in terms of looking at this plot as the voltage on the Y-axis, the current on the X-axis, Ohm's law says that the resistance is going to be equal to the slope. When you have ohmic materials, what you'll notice is that slope is constant. So for materials that are ohmic, the ratio of the current flowing across the resistor to the voltage that you're using to drive that current, that stays the same. For non-ohmic materials, that ratio changes. Now there may be some small range for a material that's non-ohmic where it acts reasonably ohmic. So over some small values of current, you may have a non-ohmic material where that stays relatively constant, or stays constant enough that you can treat it as if it is ohmic. We will spend most of our time in class focusing on materials that we will assume are ohmic. Of course, if this equation defines resistance, then that also tells us, or gives us, an equation for figuring out what the units of resistance are. So the units of resistance will be units of potential difference over units of current. Potential difference has units of volts, current has units of amps, so the units of resistance are volts per amps, which again we give its own name. We call these ohms. And ohm, we use a capital Greek omega. So we're going to use ohm as the SI unit for resistance. Well, what does the resistance depend on? If you take any particular resistor, what matters in terms of figuring out what the resistance of that resistor is? Basically, it only depends on two things: the geometry of the resistor and the material that it's made out of. So if we think about what are known as uniform cylindrical resistors. So this is a picture of a uniform cylindrical resistor. It is what it sounds like. It says that basically you've got the material that makes up your resistor uniformly distributed along some cylinder, and the current is going to come in on one end and go out on the other. Then you can calculate the resistance of this resistor by thinking about these three parameters. So rho here is the resistivity of the material again. L is the length of the conductor. So we've built our resistor out of some material. L is the length of our resistor. What's the length of the cylinder? And then A is what's the cross-sectional area of the cylinder. So these are the only parameters, two of them geometric, one of them that's telling you about the material, that the resistance depends on. So initially, we defined our resistor as it is something that resists current flow across it. Well, another way that we can think about a resistor, sort of a second definition that we can provide, is that fundamentally what resistors do in terms of the energy in your circuit is they dissipate that energy. As that current flows across the resistor, it's going to convert the electrical energy of those charges into the thermal energy of the material that makes up the resistor. And then what tends to happen is, as the thermal energy increases, that energy gets radiated away as heat. Resistors dissipate energy by converting electrical energy into thermal energy and then allowing that thermal energy to be radiated away as heat. This is how you make toast. Right? So when you turn on a toaster, clearly you've plugged it in, you've hooked it up to some voltage source that's going to drive a current across the resistive elements of your toaster. In your toaster, as that electrical energy is converted into thermal energy, you actually see those elements turn red. Right? They get red hot, and then that increased thermal energy gets dissipated away as heat. That heat transfer is what toasts the bread that you've put into the toaster. So at a molecular level, how this happens is that the electrons that are moving around as part of the current, the free electrons that actually make up the current flowing through the circuit and therefore across the resistor, they drift in response to an applied electric field, just like we talked about with current. But the problem is they can't go very far before they hit atoms within the material. So it's basically the fact that those free electrons, as they move, are constantly jostling into the atoms that make up whatever material is making up your resistor. So how a resistor is going to take the electrical energy of the charges moving around in the current, the electrical energy provided by the current, and dissipate it away is because the kinetic energy of the electrons become converted into the thermal energy of the atoms, and then that increase in thermal energy can then be radiated away as heat. If you want to calculate out how much energy is being dissipated in a resistor, well, what we tend to do is not calculate the energy itself. What we tend to do is calculate the rate at which the energy is dissipated. That's the power. So in the same way that we would calculate the energy stored within a capacitor, we're going to calculate the power dissipated by a resistor. and that's given by the current flowing across the resistor times the potential difference across the resistor. The rate at which energy is dissipated in a resistor, the power, is equal to I times V. Well, of course, we know that we can use Ohm's law, V equals IR, to again rewrite that equation in terms of any two of those three variables we want to. So we can calculate the power as I times V, or we can get rid of the V and calculate the power as I squared times R, or get rid of the I and calculate the power dissipated as V squared over R. So all of those are equivalent expressions, just taking advantage of Ohm's law to pick which of the two variables we want to use to do our power calculation.